Hi there! Welcome to the 45th episode of the Synth project, where we are building a synth together. It is time to add the last piece of hardware to the MIDI module, the one that generates control voltages based on the reception of control change messages. These messages will allow manipulating controls on the synth, like volumes, frequency ranges, glide duration, and in general all those parameters that provide modification to the sound generated by the VCO. Let's begin! Control change messages are usually created by a MIDI controller in response to the adjustment of a potentiometer. The current position of the potentiometer is provided with the last data information in the MIDI message. We can use such information in our synth to generate a corresponding control voltage that we can use for several purposes. From simply adjust the pitch of a sound waveform to the control of various parameters in the synth, like the volume level of a VCA channel, the duration of the glide, the depth of a frequency modulation, or the frequency of an LFO. Since we need to create a control voltage, we will have to perform once again a digital to analog conversion to transform the digital information in the MIDI message into an analog control voltage. Problem is, we have already used both of the two digital to analog converters available on the Arduino Due. However, the Arduino Due allows us to make a digital to analog conversion using another of its features, although we will need to add some external hardware to complete it. This feature is the capability of generating PWM waveforms. Practically, we can assign a data pin with PWM capability to each of the control device numbers we want to handle, and since I have an Akai LPD8 with 8 of such devices, I will add to the MIDI module the capability of handling up to 8 control devices simultaneously. All well then, but what is this PWM feature we are talking about? Basically, a PWM signal is a square wave at a fixed frequency with a variable duty cycle. If we change the duty cycle between 0 and 1, we obtain an average value of the wave amplitude that goes from 0 to its maximum value, which is 3.3 volts for the Arduino Due. By simply forcing such a signal into a low-pass filter, we can extract the average value and therefore obtain a DC voltage proportional to the CC value from the MIDI message. Let's take a look now at the software needed to handle the control change messages. First software changes to the existing code begin on line 113, where we define the data pin number used for each of the 8 control devices we want to handle. As you can see, we will use pins from 2 to 9, which are 8 of the available 12 PWM pins on the Arduino Due. Next, we jump to line 362, where I have defined a function that associates a device number with a specific pin of the Arduino. Right now, these associations are hard-coded, which means they are written to stone in the code and cannot be changed. In a future release of the MIDI module software, I will make it possible to change the associations by giving to the user the possibility of programming such associations on the fly. For now, however, I will leave them fixed. If you are planning to build the MIDI module for yourself, and you happen to have a different MIDI controller that provides different device numbers, you will just need to capture such numbers on the module LCD and then modify accordingly the numbers in these case statements. The devices of the LPD8 are numbered from 0x46 to 0x4d in hexadecimal, and that's why I choose these values. Note also the code on lines 390 through 398. If the received device number is not among the hard-coded ones, a warning message will appear on the LCD. Let's go now to the control change message handler, starting on line 402. I have added here a very few lines starting from 427. This line basically calls the conversion function we have seen before, passing as a parameter the data1 value, which is the one containing the device number associated with the control change message. The function will return the pin number that needs to be used for the particular device number. If such pin value is a valid one, we then call function analogWrite, which will emit on the designated pin the value provided by data2. However, since data2 is an 8-bit value, and since the PWM pin is set to receive a 12-bit value, we need to shift 5 times to the left the value of data2, so that we can obtain the full range of values for the control voltage. And that's it. As you can see, the software is structured in such a way that it is very easy to add new functionalities with just a few extra lines of code. Let's now talk about the hardware changes, which are supposed to be the last changes we will make to the module, since any further future change will only be a software change. All the new hardware changes are concentrated on the right side of the schematic, plus another page we will examine later. We have the new pin header H19, which allows us to connect to the 8 data pins of the Arduino II that we need to extract the PWM waveforms. Each pin from the Arduino goes to the input of a third-order low-pass sudden key filter, adjusted for a Q of about 1 to avoid both under and overshooting, and a cutoff frequency of about 80 Hz, which is 1 order of magnitude lower than the frequency of the PWM waveforms. The characteristics of this filter allow us to remove entirely the square wave component of the PWM waveform, leaving only the average voltage, which is what we need. Following the low-pass filter, there is also an amplifier stage with a gain of 3, needed to bring the 0 to 3.3 volt range from the Arduino II to the 0 to 10 volt range we need for the control voltages used in the Synth. The amplifier has also the added benefit to lower the impedance of the control voltage output, so it can be used by any of the modules inside the Synth without affecting its value. The same third-order filter we examined is replicated 7 more times, once for each of the control voltage outputs we are going to provide on the MIDI module front panel. We have 4 filters in this page and 4 more in the next. The output of all these filters go directly to header H6, to which we will connect all the elements of the front panel, besides of course the LCD and the push buttons, which have their own connectors. Let's now move to the lab to see how these new controls work. And here we are, and we are looking at the final prototype of the MIDI module. Here is where I mounted 2 of the low-pass filters and amplifiers to handle 2 of the 8 PWM outputs from the Arduino II. This is the TL074 containing 4 op-amps, which I have used to handle specifically the 2 devices K5 and K6 from the LPD8. I am also using K1 to generate a PWM output with no filter on it, to show how the variable duty cycle on the PWM signal works. Since I have only 2 complete filters and amplifiers, there are only 2 jack sockets on the prototype, right here. The socket on the right is connected to channel 2 of the oscilloscope, the one with the blue trace. The other channel of the oscilloscope, the one with the yellow trace instead, is directly connected to one of the ports of the Arduino, so we can watch the actual PWM output. You can see how the 3 pins I am using are occupied by the USB shield, but there is still access through the shield header. Summarizing, 1 pin goes directly to the oscilloscope yellow channel, and 1 output from the filters goes instead to the blue channel. The second filter output is finally connected to this analog multimeter, which will allow us to see in real time how the output changes when we move the corresponding potentiometer. Let's start the test by moving the controller K1, which is the one connected directly to the yellow channel of the oscilloscope. See, as I rotate the knob, the square wave becomes visible, and based on the position of the knob, the duty cycle assumes a different value, thus generating the average voltage that makes up the control voltage for that controller. and we can see also how that stays in sync with the information we get directly from the MIDI message visible here on the LCD screen. The duty cycle changes going from 0 when the knob is all the way to the left and 1 when the knob is all the way to the right. Let's now compare with the controller K5, watching the blue trace on the oscilloscope. And you can see that since we are now going through the filter and the amplifier, only the average voltage of the square wave is visible, and it changes while rotating the knob. And finally, if we use K6, we can see the effect of the analog multimeter, which shows a fluid and continuous movement of the pointer on its scale, corresponding to the movement of the potentiometer knob. So, now that everything has been designed and tested, we need to mount the whole circuit on a PCB board and assemble the module on a case made just for it, which is what we will do in the next episode. In there, we will also run a final test directly on the synth itself and maybe play some music. To avoid missing the next episode and any other future episode, please make sure that you are subscribed to the channel and that you have activated the notifications. In the meantime, I leave you with my usual happy experiments!